Let's call the next speaker, my dear friend from Milano, Dr. Claudio Tomella, who is focused on nutrition and metabolism, and he will give the talk about inflammation, mitochondria, and so on. Thank you so much, Claudio.
Buongiorno a todos. And thank you for the invitation to the organization, especially to João Pedro and Professor Nemoya. It's an honor and pleasure for me to be at this International Antiaging Summit 2023 in this wonderful location in Lisbon. Well, I am from Italy. So, what is the best solution? Ferrari or Tesla? It's difficult to choose. Ferrari is a fascinating Italian luxury car, rich in history, with a seductive sound. It is simply a Ferrari. It uses gasoline as fuel, and it doesn't work without gasoline. Tesla uses electricity as fuel, and it is performing, technological, and silent. It doesn't work without electricity. In the course of our evolution, the organism has had to choose its metabolic fuel and adapt itself to various environmental fluctuations, and to do this, it became flexible. Lipolysis, proteolysis, gluconeogenesis, and ketone bodies as alternative energy substrates provide examples by which natural selection tailored humans to manage fluctuations in energy supply. Metabolically active organs such as liver, heart, skeletal muscle, adipose tissues, pancreas, and brain communicate continuously to best organize the use of available fuel. But who selects the fuel? The mitochondria. The mitochondria is our hybrid engine that is able to use both glucose and fat as fuel. The concept of metabolic flexibility was particularly linked to the capacity of mitochondria to select fuel in response to nutritional changes. But there is a problem. Humans switch their primary lifestyles towards a plethora of energy-dense foods, persistent psycho-emotional stressors, and lack of exercise in a record time. All these changes favor decline in metabolic flexibility and favors the development of several metabolic diseases, in other words, metabolic inflexibility, and this promotes unsuccessful aging. So, in my presentation, I explore the concept of metabolic flexibility and mitochondrial function based on newly emerging data, and I give you some suggestions to improve it. Metabolic flexibility is the ability of cells to switch from a state of predominant lipid oxidation during fasting conditions to the suppression of lipid oxidation, then the increased glucose uptake, oxidation, and storage under insulin-stimulated conditions or after a meal. During the postprandial period of a carbohydrate-rich meal, pancreatic beta cells respond to the rising nutrient by releasing insulin into the bloodstream, increasing the insulin-glucagon ratio. Under the influence of insulin, the liver is triggered to absorb glucose from the circulation and stop glycogenolysis and gluconeogenesis. Adipose tissues assist in glucose clearance as insulin receptor binding of insulin results in translocation of glucose transporters such as GLUT4 to the plasma membrane, allowing glucose to enter the cell. Adipose tissue respond to insulin by decreasing the rate of lipolysis and stimulating fatty acid synthesis for lipids and glucose. During fasting, the decrease in circulating dietary carbohydrates and lipids and the decline in insulin-glucagon ratio induces a switch toward fatty acid oxidation. Glucagon stimulates the hepatic glycogenolysis and ketogenesis, and the decrease in insulin suppresses malonyl-CoA synthesis and lipogenesis with concomitant activation of fatty acid oxidation. Because the adipose tissue is the predominant source of free fatty acids, the capacity of adipose tissue to store fatty acid during caloric availability and release fatty acid during caloric restriction is an important determinant of metabolic flexibility. It's not trivial. What happens with caloric excess? With caloric excess, the mitochondria are overwhelmed by an excess in substrates derived from fatty acids, glucose, and amino acids. This leads to mitochondrial metabolic indecision, resulting in incomplete substrate utilization for energy production and consequent storage of substrates in ectopic depot. In conditions of substrate overload, the mitochondria must make a choice between acetyl-CoA delivered by either pyruvate dehydrogenases or the beta oxidation. This results in elevated levels of acetyl-CoA. And other acetyl-CoA at crucial sites where the catabolism of fatty acids, glucose, and amino acids converge, leading to a state in which upstream substrate catabolic flux slows down considerably, a phenomenon coined as mitochondrial metabolic gridlock. In addition, the continuous influx of fuel leads to the accumulation of reducing equivalents in the mitochondria and an increase in the mitochondrial membrane potential. These changes create a microenvironment that promotes the generation of reactive oxygen species and other metabolites that leads to protein modifications, cellular damage, and chronic diseases. Skeletal muscle. To understand the importance of skeletal muscle, just consider that the term of metabolic flexibility was coined by Kelly and colleagues in 1999 when they studied fluid selection in skeletal muscle in lean and obese individuals after an overnight fasting. They discovered that skeletal muscle of lean individuals showed a remarkable ability to adapt fuel preference to fasting and insulin infusions, and they were defined as metabolically flexible. We know that skeletal muscle consists of oxidative type 1 and glycolytic type 2 fibers, which differ in their metabolic capacity. During low-intense exercise, oxidative muscle fibers predominantly rely on fatty acid oxidation. During more intense exercise, the rising ATP utilization rate induces a switch from fatty acid oxidation to glucose metabolism. During acute exercise, an increased AMP-ATP ratio sensed by the AMPK increases the activity of the PGC1-alpha, that is a major regulator of exercise-induced adaptations in skeletal muscle. Several studies support the idea that the regulation of mitochondrial function underlies the development of metabolic inflexibility. Mitochondria are pliable organelles, and they adapt their morphology to nutrient availability, and in doing so, regulate substrate preference. Mitochondrial morphology is dependent on nutritional status of the cell. Cells exposed to a nutrient overload have a fragmented mitochondrial network, whereas upon calorie restriction, mitochondria appear more interconnected. Increasing mitochondrial elongation and interconnectivity induces a metabolic adaptation that increases ATP synthesis capacity and efficiency, whereas fragmentation of mitochondrial network reduces bioenergetic efficiency and might protect against the detrimental effects of nutrient overload. Mitochondrial dysfunction is intimately linked to senescence and senescence-associated secretory phenotype, which involves the secretion of multiple factors such as pro-inflammatory cytokines, proteases, and growth factors that have potent effects such as inflammation and cancer. Metabolic flexibility is negatively correlated with aging. Several age-related changes such as mitochondrial dysfunction, muscle deterioration, cellular senescence, hyperinsulinemia, and inflammation affect metabolic flexibility simultaneously. Systemic inflammation and metabolic inflexibility can cause a vicious circle, because systemic inflammation can also trigger metabolic inflexibility. To maintain energy or homeostasis, different tissues secrete factors such as adipokines, myokines, hepatokines, and patokines. We know that adipokines such as leptin and adiponectin provide signals in response to changes in energy storage. The adiponectin-leptin ratio is used as a biomarker of adipose tissue dysfunction. Myokines such as myostatin and myonectin act as a communication signal for skeletal muscle to regulate the whole body metabolism during exercise. For example, exercise decreases the expression of myostatin in humans, and obesity is associated with increased myostatin expression. Hepatokines such as FGF21 and phytin A can also regulate metabolic flexibility. For example, phytin A has a major role in the regulation of insulin sensitivity, as phytin A deficient mice showed improved insulin sensitivity. Patokines produced by the brown adipose tissue are involved in the regulation of body temperature and energy expenditure via thermogenesis, sympathetic nervous system activity, and brown adipocyte hyperplasia. Interestingly, some of these paracrine and endocrine factors are secreted by multiple tissues, and their local function and impact on metabolic flexibility can depend on their origin and local plasma concentration. For example, interleukin-6, when secreted by skeletal muscle, stimulates AMPK activity and in this way increases glucose uptake and beta oxidation in muscle and adipose tissues. Whereas when interleukin-6 is secreted by adipocytes from obese patients, it negatively affects metabolic flexibility by decreasing insulin signaling glucose uptake because of its pro-inflammatory properties. Now, we explore how metabolic inflexibility can be reversed by lifestyle and pharmacological intervention. Your mitochondria are what you eat and depends on your diet. Historically, this area of study is divided into opposing viewpoints that argue for or against the idea that it is healthier to burn fat than glucose. Recently, these two camps have found common ground in the concept of metabolic flexibility, which posits cells function optimally when they retain their capacity to switch freely between oxidative substrates. Importantly, a certain data intervention will have different effects on different individuals. In other words, different individuals may follow different trajectories towards improved health, positive aging, and longevity. These trajectories may depend, for example, on individual epigenetic regulation, human constitution types, lifestyle, stress, and on the national functional level. So, moving beyond from the standard recommendation to eat less and move more, we have personalized nutritional approach. But what does personalized mean? Food choices people make every day are based on a complex combination of preference for taste, smells, habits, and are influenced by culture, relationships, and beliefs about food. We need to take this into account. Palmer, a professor at Texas University and one of the world's leading experts on metabolic flexibility and metabolism, gives such interesting suggestions for improving metabolic flexibility in this review published by Mayo Clinic Proceedings just a few months ago. Therapeutic approaches To maintain energy balance and mitochondrial function, focus on three factors: reducing energy intake with calorie restriction and intermittent fasting, boosting the capacities of the systems that mitigate mitochondrial stress, and reducing energy expenditure with exercise, cold exposure, hypobaric hypoxia, and SGLT2. There are a plethora of emerging data on the positive effects of intermittent fasting on metabolism, mitophagy, and longevity. Both aerobic and anaerobic activity promotes considerable health benefits, such as improved mitochondrial content and metabolic flexibility. Don't forget that temperature as well as circadian clock can favorably influence metabolic flexibility. The pharmaceutical approaches to improve metabolic flexibility have been studied in great detail. Several evidence suggests that boosting the capacities of the systems that mitigate mitochondrial stress, such as glutathione, carnitine, NAD, AMPK, citrulline activators, and uroletin A, spermidine, provide a useful strategy to stimulate metabolic flexibility and mitochondrial function. Mitochondria is what we eat. We must absolutely avoid mitochondrial indecision as well as mitochondrial metabolic gridlock. Preserve the ability of mitochondria to select fuel in response of nutritional changes. Healthy lifestyle and personalized medicine can influence metabolic flexibility and mitochondrial function and favor positive aging and longevity. Thank you for your attention.